Hello everyone. So today we're going to talk about shear stress. Okay, shear stress within a fluid. So let's take this for example. Okay, you have a bottom layer, a bottom solid surface. Okay, that is stationary and is not moving. And then on top right, you have another solid flat surface that is moving in from the direction of left to right. And this gap in between has a height of, say, L. Okay, so this is L. Okay, and the top surface is moving at, say, U, capital U over here. So if we draw a two axis, right, Y against U, you will be able to plot this blue line over here. Okay, so in fact this is the speed of the fluid in between these two surfaces. Okay, you will see that as the fluid particles that are closer to the stationary surface will tend to be going towards zero, and as you go higher, the speed increases, the velocity increases, until the fluid particle that is just next to the moving surface will inherit the value of the velocity of the top surface, which is u. Okay, so this blue line is effectively the velocity profile. Okay, I can draw a y-axis, I can draw a u-axis, and this will be the velocity profile of the fluid within the two surfaces. Okay, and we can see that this is a linear straight line, and there is a certain gradient to this line, right? And what we say about shear stress, which is tau, is that it is equals to the dynamic viscosity of that fluid multiplied by the gradient of the straight line, of the blue line. Okay, and the gradient, the change in velocity over the change in height. So the change in velocity is from 0 to capital U, so it is capital U. Change in height is from 0 to L. Okay, so it is U over L. So this will be in a unit of Newton per meter square, because shear is a force per unit area. Okay, similar to a pressure. Okay, pressure is a normal force. Shear is a tangential force. Okay, and once you get the value of shear stress, you can actually find the shear force. Okay, shear force is simply shear stress multiplied by the area of contact of that shear face. Okay, so it is just tau multiplied by area. You get a force value, which is newtons. Okay, so if this is a moving surface, and why it moves is caused by a force that is pulling from left to right. If there is a pulling force involved to make this surface move at the velocity capital U, okay, this pulling force will be your shear force. Okay, because this is the force that is used to overcome the shear stress. So you can say that the pulling force is equals to the shear force, okay, which is equals to tau multiplied by area. Okay, and another observation that you can actually get from this diagram, right, is that at any height, okay, at any height, you are actually the fluid is actually experiencing the same velocity gradient. Here the gradient is u over L. Here the gradient is also u over L. Here the gradient is also u over L. So what does this mean? It means that at any fluid layer, okay, no matter which layer you are looking at, okay, the shear stress is always the same value, because this line has a constant gradient, and this dynamic viscosity doesn't change as well. So this whole thing will always be constant.